Hi everyone, myself Chandragupta Reddy from the Department of Electronics and Communication Engineering. Today we are discussing about Introduction to Classical Control Design Techniques from the subject Control Systems. Introduction. First of all, we have to know about what is control systems. A control system is a system that manages commands, directs or regulates the behavior of other devices or systems. Control systems are found in engineering, automation and process industries. Types of control systems: open loop and closed loop feedback control systems. Classical control theory overview. Classical control focuses on the time domain and frequency domain responses of a system, primarily used for signal input and signal output. It's simply called as SISO systems. Key objective: to achieve desired system behavior with acceptable stability and performance. Key classical design techniques: Root Locus, Bode Plot, Nyquist Plot, time domain analysis. First one, Root Locus Method. A graphical Root Locus Method is a graphical technique for examine how the roots of characteristic equation, poles of the closed loop transfer function change as system parameter typically gain is varied. Use it to analyze stability and transient response. Key points: determines system stability as the system gain changes. So how system poles and zeros move in this S-plane. Second one, Bode plot. Content. A Bode plot consists of two plots, magnitude plot and phase plot. It is used to analyze the frequency response of a system. It provides insights into system gain, phase margin and bandwidth. Key points: stability analysis using gain and phase margins. Design controllers like PID using frequency response. Third one, Nyquist Criterion. Nyquist Criterion is used for stability analysis of a open loop systems. It involves plotting the frequency responses of the system and analyzing the encirclements of this critical point -1, 0 in the complex plane. Key points: determines the stability of a system with feedback, helps to avoid instability in closed loop systems. Fourth one, time domain analysis. Time domain methods involves analyzing the response of the system to standard inputs, example step impulse or ramp. Key parameters: overshoot, settling time, rise time and steady state error. Key techniques: transient analysis, analyzing how the system behaves in the time domain after a disturbance. Steady state analysis, the long-term behavior of the system. Time domain specifications. It is classified into 6 types. They are delay time, rise time, peak overshoot, settling time, steady state error. PID control. The proportional integral derivative, it is simply called as PID controller, is the most commonly used controller in classical control. It adjusts the control input based on the proportional, integral and derivative actions to minimize the error. Key points: proportional, it is denoted as P. It corrects the error based on the current value. Integral, it denoted by I. It corrects the accumulated past errors. Derivative, it is denoted by D. Corrects based on the future error predictions. Design example. Walkthrough of a simple system design using one or more of the classical control techniques. Example: designing a controller for a second order system using Root Locus and Bode Plots. Example: design a PID controller for a simple first order system. Limitations of a classical control. Classical techniques are limited to SISO, single input and single output systems. Difficulty in handling systems with significant time delays or multiple inputs or outputs. Not always suitable for highly nonlinear systems. Summary. Classical control design focuses on methods like Root Locus, Bode Plot, Nyquist Criterion, and time domain analysis. These techniques provide effective control solutions for simple systems but have limitations in more complex multi-input and multi-output MIMO or nonlinear systems. Understanding these techniques forms the foundation for more advanced control methods. Compensators. A compensator is a device or control used to improve the performance of a control system by altering its dynamic response. The primary goal of a compensator is to modify the open loop transfer function in a way that improves the stability, transient response, or steady state error of a system. Compensators are often added to the system to achieve desired specifications such as increased stability, reduced overshoot, or faster settling time. Key points. Compensators adjust the system response in both time and frequency domains. They can be implemented using various components like controllers, like PID, lag or lead controllers, or filters. Types of compensators. They are classified into three main types of compensators commonly used in classical control design. Proportional derivative. It is also called as PID compensator. Purpose. Increases the system damping and improves the transient response. Effect. It reduces overshoot and improves the speed of response. Transfer function. GC of S equals to Kp plus Kd GC of S is equals to Kp plus Kd S. GC of S equals to Kp plus KDS. When to use? When the system needs a faster response with minimal overshoot. Second one, proportional integral compensator. It's simply called as PI compensator. Purpose. Reduces steady state error, especially for constant disturbances, but may introduce slow response dynamics. Effect. Eliminates steady state error for step input but can affect system stability. Transfer function. GC of S equals to Kp plus KIS SG C of S is equals to Kp plus fraction of Ki S GC of S equals to Kp plus SKI. When to use? When steady state error must be minimized and the system can be tolerated a slower response. Third one, proportional integral derivative PID compensator. Purpose. Combines the benefits of PD and PI controllers to improve both transient and steady state response. Effect. Provides faster response, reduces overshoot and eliminates steady state error. Transfer function. GC of S equals to Kp plus KIS plus KDS GC of S is equals to Kp plus fraction of KIS plus KDS GC of S is equals to Kp plus SKI plus KDS. When to use? Ideal for systems requiring both fast response and zero steady state error. Types of compensators. In that first one, lead compensator. Purpose. Increases the phase margin and speed up the system response by adding positive phase shift. Effect. Improves transient response without affecting the steady state error much. Transfer function. GC of S equals to Ks plus Zs plus PGC of S equals to K fraction S S plus Z, S plus P, GC of S equals to Ks plus Ps plus Z, where modulus Z less than or equals to modulus P modulus Z, less than or equals to modulus P modulus Z. When to use? When you need to improve the speed of response and phase margin. Second one, lag compensator. Purpose: increases steady state accuracy by adding negative phase shift at low frequencies. Effect: improves system stability and reduces steady state error, but may slow down the system. Transfer function: GC of S equals to Ks plus Ps plus ZC of S equals to K by fraction of S plus P, S plus Z. JC of S equals to Ks plus Zs plus P. When to use? When steady state error needs to be minimized without drastically affecting the transient response. Third one, lead lag compensator. Purpose: combines the effects of both lead and lag compensators. Effect: balances the improvement in phase margin and steady state error. When to use? When the system requires both improved transient response and reduced steady state error. Compensator design approach. The design of compensator typically involves system analysis. Means study the open loop transfer function and decide the specifications. Choosing the compensator type based on desired improvements, example faster response, reduced error, etc. Frequency domain analysis. Using Bode Plots and Nyquist Plots to analyze phase margin, gain margin and stability. Tuning parameters. Adjusting the compensator parameters to achieve the desired performance. Key steps in designing. Determine the system performance issues like overshoot, settling time, etc. Choose the appropriate compensators like PD, PI, PID, etc. Design the tune the compensator using Root Locus, Bode Plot or other classical methods. Summary of compensators. PD compensators. Improves transient response by adding derivative action. PI compensator. Eliminates steady state error with integral action. PID compensator. Combines with both PD and PI for over performance improvement. Lead compensator increases speed and phase margin. Lag compensator reduces steady state error at expense of speed. Lead lag compensator balances the effect of lead and lag for optimized performance. Thank you.